Hey everyone, welcome. Have you ever felt like there's got to be a better way to teach science than just having students memorize facts? Well, you are definitely in the right place. Today, we are going to break down the framework for K-12 science education. It's basically the blueprint for creating these incredible, phenomenon-based lessons that your students will never forget. Okay, let's just jump right in with the big question, the one that really gets to the heart of all this. Is science just a big pile of facts that we need kids to memorize? For a long, long time, that's kind of what it felt like in a lot of classrooms. And that's exactly the mindset we're here to flip on its head. In this slide, wow, it just lays it out perfectly, doesn't it? On one side, you've got the old way. Science is just this random assortment of facts, and students are basically empty vessels waiting for us to pour the information in. But look at the new vision. This changes the entire game. Science becomes a way of figuring out the world, and our students, they get a new job title: active investigators. They become the scientists. And you don't have to take my word for it. This quote from the framework itself just nails it. We're not teaching a miscellany of facts, we're helping students build a coherent body of knowledge. And that knowledge isn't just something to know, it's a powerful tool they can actually use. So how in the world do we make this happen? How do we get from just knowing the what to really understanding the how? Well, this new vision is built on three essential dimensions. And the key is that they're all woven together in every single thing we do. This is the recipe for what we call three-dimensional learning. Let's dive into the first dimension, the scientific and engineering practices. The best way to think about this is that it's the doing part of science. We're moving past just telling students what scientists do, we're actually letting them be scientists. The framework sees what scientists do as this really cool continuous cycle. It all starts with investigating. You see something in the world, you ask questions, you gather some data. Then you move into developing explanations for what you've observed. But it doesn't stop there. The crucial third part is evaluating those ideas, critiquing them with evidence, which, of course, just leads to brand new questions. And the whole cycle starts again. And inside that cycle, this is what students are actually doing. They're building these incredible skills. We're not just handing them a cookbook lab anymore. They are learning to ask their own questions, to build models that show their thinking, and, this one's so important, to argue from evidence. This is what real science looks like. All right, so that's the doing. Let's move on to the second dimension. If the practices are the hands-on part, the cross-cutting concepts are all about the thinking. These are the big ideas, these intellectual lenses that actually connect all the different branches of science. So, what are these secret keys to scientific thinking? Here they are, the Magnificent Seven. Think about it. It doesn't matter if you're a biologist studying cells, an astronomer studying galaxies, or a physicist studying motion. You are always looking for patterns. You're trying to figure out cause and effect. You're thinking about systems. These concepts are the common language that unites all of science. Let's just zoom in on one of these, like cause and effect. See, it's not enough to just say, this causes that. The real science, the real power is in figuring out the mechanism, the step-by-step story of how this causes that. Because once you understand the mechanism, you can start to make some seriously powerful predictions. Okay, that brings us to our third and final dimension, the disciplinary core ideas. You can think of this as the knowing, the absolute must-have content, the foundational knowledge for any specific field like physics or chemistry. And for all you physics teachers out there, this is a game changer. The framework helps us cut through the noise and focuses the entire subject down to these four big core ideas. So instead of a massive checklist of topics, we get to build our courses around these huge pillars: matter, motion and forces, energy, and waves. Take a look at PS2, motion and stability. The point here isn't just for a student to be able to write down Newton's second law. No, the goal is so much bigger. It's for them to truly understand forces so deeply that they can explain why things move and predict whether a system will be stable or not, whether that system is a tiny atom or an entire galaxy. Now, that is a powerful idea. So, we've got our three key ingredients, right? The practices, the cross-cutting concepts, and the core ideas. But here's the most important part of all. You never, ever teach them alone. The real magic, the deep learning, it only happens when you weave them all together in every single lesson. This is it. This is the formula for three-dimensional learning. Students are doing science with the practices, they're thinking like scientists using the cross-cutting concepts as their lenses, and they're doing all of it to make sense of the core knowledge of the subject. It's the whole package. And when you start braiding those three dimensions together, this is the kind of amazing lesson flow you get. You don't start with a list of vocabulary words. You start with a phenomenon, something real and observable that makes students go, huh, why did that happen? That curiosity then drives them to ask questions, explore, and build their own models to explain it, using those practices and concepts to really understand the core idea. And it goes without saying, if we're going to change how we teach, we absolutely have to change how we assess. A three-dimensional assessment doesn't just ask a student to define a word from memory, no way. It gives them a new situation, a new problem, and asks them to use what they know to figure it out. It's all about assessing what students can do with their knowledge. So when you zoom all the way out, what's the point of all this? The ultimate goal here isn't just to create a few more professional scientists, as great as that is, it's so much bigger. It's about raising an entire generation of scientifically literate citizens, people who can think critically, who can evaluate evidence, and who can be thoughtful participants in a world that is completely shaped by science. And that brings it all right back to you, in your classroom. This entire framework is designed to empower you, to shift from being the person with all the answers to being the guide who helps students find the answers for themselves. So really, the only question left is this. What amazing, compelling, puzzling piece of the world are you and your students going to investigate first?